Oh, welcome and thank you for joining. Let's take a look at a homework question. This is from lesson U5, L5A, number 16, or you can find it in the textbook, Nelson textbook, on lesson 8.5, question number 16. So in this question, we're asked to find an equation of the plane that is perpendicular to the plane x plus 2y plus 4 equals 0. It contains the origin and has a normal that makes an angle of 30 degrees with the z-axis. So let's read the question for a second time and try to figure out or sort out the information given. So we are asked to find an equation, and whenever you are asked to find an equation or a variable, it means that chances are there are more than, or there is more than one possibility, so more than one solution. So we are trying to find an equation of a plane that is perpendicular to the plane x plus 2y plus 4 equals 0. So this is a given plane, and we are trying to find the equation of a plane that is perpendicular to it. So we are dealing with two different planes. So as we read, we are going to start jotting down the information, and in the meantime, obviously, organize it. And my favorite way of doing this, whenever we are dealing with questions that involve two things of the same nature, for example, two planes or a line of a plane or two lines, is by creating a T-chart. So I will make a T-chart here, and in the first column, I'm going to put information about the first plane, and second column, information about the second plane. Now, this first plane in here, x plus 2y plus 4 equals 0, is the given plane. I'm going to call this plane pi 1. Now, the second plane that we are trying to find has the following characteristics. It contains the origin, has a normal that makes an angle of 30 degrees with z-axis, and is perpendicular to the plane. So there are three different specific pieces of information that are given about the second plane. And since we do not know the equation of the second plane, and that's what we're trying to find actually, so we're going to call this a plane pi 2 with scalar equation ax plus by plus cz plus d equals 0. So once we have identified or given a name to the two bigger pieces of information or objects that we are dealing with here, then we will write the characteristics of each plane right underneath it. So about plane pi 1, we only know the equation. We can quickly derive the normal to the equation of the plane, or normal to the plane. And we know that we obtain the normal by looking at the coefficients of x, y, and z. So as you can see here, x has a variable, a coefficient of 1. Y has a coefficient of 2, and z doesn't even appear in the equation, which means that the coefficient of z must have been 0. So that tells us that the normal to plane pi 1 would have the coordinates 1, 2, and 0. Remember, this is one of the normals we can identify or we can use. So another normal can be, for example, a multiple of 1 to 0, for example 2, or double of 1 to 0, or negative 3 over 2, 1 to 0, or root 3, 1 to 0. So any multiple of 1, 2, and 0, vector 1, 2, and 0. Now, about plane pi 2, we have a lot more to say. So number 1, plane pi 2 is perpendicular to plane pi 1. So the two of them are perpendicular to each other. The second piece of information is that plane pi 2 contains the origin. So we're going to say that we have a point on pi 2 with coordinates 0, 0, and 0. And plane pi 2 has a normal that makes an angle of 30 degrees with z-axis, so we'll write that down as well. So the following three pieces of information will help us determine the equation of plane pi 2. We're going to start using these pieces of information one at a time. So we're going to say that since plane pi 1 is perpendicular to pi 2, therefore the normal to plane pi 1 dotted with a normal to plane pi 2 must equal 0. So the normal to plane pi 1 we already determined, it is 1, 2, and 0. Whereas the normal to plane pi 2 will be defined by the coefficients of x, y, and z, which means that n2 must be a, b, and c. And the dot product of these two normals would be equal to A plus 2B plus 0C equals 0. So remember that to dot product two algebraic vectors, because normals are practically vectors, right? Or represented by vectors. So all we have to do is multiply the x's together. So 1 times A is A, multiply the y's together. So 2 times B is 2B, and multiply z's together. So 0 times C is 0C. So in a more simplified form, then we're going to have A plus 2B equals 0. So we have disclosed a relationship between A and B, and it only makes sense to express one of the coefficients of the normal for plane pi 2. So express A in terms of B, and we can easily do this by taking 2B to the other side. Similarly, you can express B in terms of A, but whenever we do that, we try to be wise in our choices in terms of the coefficients that we obtain. So we try to eliminate or to avoid using fractions because they will make the expressions a little bit more awkward. So with this, then we're going to say that we have used all we can for now from the first piece of information given, so pi 1 perpendicular to pi 2. So we're going to take a look at the second piece of information. So there is a point with coordinate 0, 0, 0 on plane pi 2. So what that means is that since the point P with coordinate 0, 0, 0 is on pi 2, then x equals 0, y equals 0, z equals 0 must satisfy the equation of plane pi 2. So therefore, we're going to say that ax plus by plus cz plus d equals 0 at point P will be a times 0 plus b times 0 plus c times 0 plus d equals 0. So if you solve this equation for the coefficient d, notice that this is 0, 0, 0. So we obtain d equals 0. So with this, then, we have added more light to the equation of the plane pi 2, of the second plane. And we're going to say that plane pi 2 is in the form ax plus by plus cz equals 0. So with this, again, we have exhausted the ways in which we can use the information that point P is on pi 2. And now we're going to move on to the last piece of information, which states that the normal to plane pi 2, which is basically vector ABC, and the z-axis make an angle of 30 degrees with each other. So there is a lot to talk about in this case. So we're going to say that since the normal on N2 and the z-axis make an angle of 30 degrees with each other, therefore we're going to say that the direction vector of z-axis with N2 would make a 30-degree angle. So basically, we want to express N2 and the z-axis in vector form. And the best way to represent z-axis in vector form is by taking the direction vector of it. Now, I want you to think for a second. So what can be a direction vector of z-axis? So remember that on the z-axis or on any axis, two of the coordinates will be 0, and only the coordinate that is on the z-axis can be different than 0. And as a matter of fact, we can take in this case x equals 0, y equals 0, and z equals 10. Or we can make z equal to 5. It doesn't really matter. Or we can make z equal to negative 2. Or we can make z equal to square root of 11. It doesn't really matter what z is, but obviously we want to work with simplest numbers possible whenever we have a chance, whenever we are given the options. So guess what? In this case, as a direction vector for z-axis, we're going to take its unit vector 0, 0, 1. Now, vectors n2 and vector r that represents z-axis now will make an angle of 30 degrees with each other. And what else but the dot product can help us figure out how the coefficients are related or the coordinates are related. So guess what? We're going to say that since the two vectors will make a 30-degree angle with each other, then we're going to say that vector n2, so the normal to plane pi 2 with coordinates a, b, and c, and z-axis that is represented by vector 0, 0, 1 will have the dot product equal to magnitude of n2 multiplied by magnitude of r multiplied by the cosine of the angle they make with one another. So now let's substitute n2 by the coordinates ABC. Let's substitute r by 0, 0, 1, and that would equal. Now remember, the magnitude of n2 will be the square root of a squared plus b squared plus c squared, and that is just the formula for the magnitude of any vector. And multiplied by magnitude of r, we know the coordinates of r, so 0 squared plus 0 squared plus 1 squared. And we don't really have to go through this down this path because we know that we chose a unit vector on the z-axis, which means that the length of the unit vector will be equal to 1, but I just added this for clarity. And then cosine of angle 30 is equal to square root 3 over 2. It's a special angle. So let's start multiplying these two algebraic vectors, see what we get. So we're going to say A will multiply 0, and then B is multiplying 0, so B times 0, and then C is multiplying 1, so C times 1, would be equal to A squared plus B squared plus C squared multiplied by the square root of 0 squared plus 0 squared plus 1 squared is 1, multiplied by the square root of 3 over 2. So we have to clean up this expression a little bit now. So we'll simplify each side, see what we get. So on the left side, we have 0 plus C times 1, which is simply C. So C equals. And then we have square root of A squared plus B squared plus C squared multiplied by, obviously, 1 times root 3 over 2 is root 3 over 2. So we have disclosed a relationship between C and the magnitude of the normal vector n2. And we're going to say that it's best that we write them in ratio form. So we'll divide both sides of the equation by a squared plus b squared plus c squared inside square root, which would equal square root of 3 divided by 2. Now here we're going to pause for a second and we're going to think, what happens next? Because there is so many variables or unknowns, let's call them, because they do represent coefficients, and we normally use the term variables for x, y, and z in this case. So we have so many unknowns in here in the same equation, and we have built this relationship between these unknowns based on the information we were given before. So informations from informations that we call 1 and 2. So we are exhausting all the rest of connections that may exist between the coefficients. So what can we do from now? So before I express my ideas about how to approach the problem at this point and this step, so I want us to recall again how whenever we determine the equation of a plane in scalar form, ax plus by plus cz equals 0, now this will be an equation of the plane because we can express the equation of a plane in multiple forms, actually in infinite number of forms. So if we have, for example, and this is just an example unrelated to what we are doing, x plus y plus z equals 0, that would be equivalent to 2x plus 2y plus 2z equals 0. So if we were given the relationship that all of them were equal, then we would say, okay, so let one of them be a number and the rest will follow because we know that they're equal. Or if we had x plus y plus z equals 0, and we would create another equation, say for example, square root of 2x plus square root of 2y plus square root of 2z. That can be another equation. Or you can throw in a negative in front of them. That's another equation. And all these equations we're talking about are equivalent to x plus y plus z equals 0. So whenever we are at a point where we want to determine what the coefficients, the three coefficients of an equation in the scalar equation of a plane is, so what we can do is we can let one of the coefficients be a number, let's say the coefficient c be a number, and then we can use the relationships that exist between c and the other two coefficients so that we can complete the equation, and they will complement each other because what's important is that they follow the relationship, the same relationship that we use to determine them, a relationship that exists between them, and we use to determine the values of a and b subsequently, and we can create an equation of the plane in this case. So the reason why I'm throwing in this idea is because my first idea here, so I'm going to explain actually two options, is we can let c be any number. And the reason why, again, is because c can be any number and a and b will follow based on the relationship that exists between them, relationship described by this very equation. And in this case, what I would do is I would let c be exactly square root of 3. I could let c be equal to a number 1. But if I let c be equal to 1, then I would have a radical expression equal a fraction, and it will be more complicated to kind of determine or use this relationship to determine a and b. But if we let c equal to a root of 3, then automatically we can say that a squared plus b squared plus c squared in square root would be equal to positive 2, and 2 is an easier number to deal with. Now, if c equals a root of 3, we can determine the rest of the coefficient based on it. And again, and I'm repeating myself and my explanations from before, we can do this because the multiples of ax plus by plus cz equals 0 can create equivalent equations, actually an infinite number of equivalent equations, okay? That's why we take this freedom. Now, another option is by simply letting the, by simply letting the value of, wait a second. So let's finish this idea first. So if c equals root of 3, then we'll have a root of 3 here over square root of a squared plus b squared plus c squared equals root 3 over 2. And automatically that can set a squared plus b squared plus c squared square rooted equal to positive 2. Another idea that, or another method that we can use is by letting the magnitude of the normal be equal to any number. And in this case, we would say that the easiest way to do this is by letting the magnitude be equal to some number 2. You can let it equal to root of 2. You can let it equal to 100. But again, if we do that, then we would get a more complicated value for c. So if we let this be, let's say, equal to 100, c would be 100 root 3 over 2 or 50 root 3. So it makes c a little bit bigger than what we want it to. And we want to write the equations in the most simplified form. So we can either go the root of letting c equal root 3 and determine a squared plus b squared plus c squared square rooted, or determine or letting the magnitude of the normal equal 2 and then determine c. So if we go down this path, then we're going to say that c divided by the magnitude of the normal, which is basically this number here, which we made it equal to 2, would be equal to root 3 divided by 2. So, and c would be equal to root of 3. So as you can see, in both ways, then we're going to say that we obtain the same values for both c and the magnitude of vector n2. So at this point, then we're going to go back to the information we were given. Remember that, again, if a squared plus b squared plus c squared, square root it equals 2. So if the square root of this expression equals 2, if we want to actually get rid of the square root, we can square both sides, and then we can get here, in this case, 2 squared, which simplifies to a squared plus b squared plus c squared equals 4. Now remember that one of the relationships that we disclosed in the previous steps was that a was equal to actually negative 2b, but it doesn't really matter in this case because when squared you still get the a positive number. So a is equal to negative 2b, and we used the fact that the two planes are perpendicular to each other, and b is b, so b squared, and then c is root of 3 squared, so that would equal 4. So as you can see, we have arrived to an equation with one variable, a single variable. So remember what we said before. So we let c be a number, and the rest will follow whatever relationship, based on whatever relationship exists between them. So we know that a is negative 2b, so you substitute, and that can give us the value of b exactly. So continue solving this equation. We get 4b squared, and then plus b squared plus 3, because square root of 3 squared is 3, and that would be equal to 4. Simplify, 4b squared and b squared make a 5b squared, and then take 3 to the other side. 4 minus 3 equals 1. So that will give b squared equal to 1 over 5. And b would be plus or minus the square root of 1 over 5. So that would be the square root of 1 over 5. Sorry. Now, next we are going to determine the value of a b based on the solution. So if b squared equals 1 over 5, I shouldn't have written this. So if b equals 1 over root 5, then a, which is negative 2b, will be equal to negative 2 over root 5. So therefore, we're going to say a is negative 2 over root 5, b is 1 over root 5, c equals root 3. And that tells us that we have disclosed all three coefficients of the plane pi 2, which will make the equation of plane pi 2 negative 2 over root 5x plus 1 over root 5y plus root 3z equals 0. So next we are going to continue with the second possibility. So b can be positive 1 over root 5, or it can be negative 1 over root 5. So if b is negative 1 over root 5, it means that the value of a would be equal to negative 2b. So negative 2 times negative 1 over root 5. So that will make the value of a in more simplified form 2 over root 5. And with this, then, we have disclosed all the three coefficients. So a is 2 over root 5, b is negative 1 over root 5, and c equals the square root of 3. So therefore, we're going to say that another form of the equation of this plane, plane pi 2, would be 2 over root 5 plus negative 1 over 5 root y plus root 3z equals 0. So these are the two equations that we obtain for plane pi 2. So again, are these the only two equations? The answer is no. So we're going to say that you can multiply here by root 5. So if we multiply by root 5, then we would get negative 2x, and then plus 1y, and then plus root 15z equals 0. Here goes another equation. Can we change this even more? You can multiply by 100 every term, and you can get a different plane, and so on and so forth. So I hope this made sense in some ways, and I hope that you found the instructions useful. Um, and bye for now. Enjoy the rest of the day wherever you are.